Hello, this is Professor Dan Kernler of Elgin Community College again. This is another video in my statistics series. In this one, we are analyzing the least squares regression line. All right, let's get to it. We're going to start this video learning about a new plot and how it can help us analyze whether a linear model is appropriate for a given set of data. So we already have our scatter plot where we have the predictor variable on the horizontal and then the response variable as the y. So this is our scatter plot. Say we have some points in here that look like this. The least squares regression line, the equation looks something like that. What we want to do now is focus on those residuals. And what if instead of making a plot of the points, we instead make a plot of the residuals? So if we kind of clean this up a little bit and take out the marks of the residuals, this is called a residual plot, where the y-axis is the residuals. What that means is then the middle of the y-axis is 0. Some points are above the line, some are below. So 0 is that middle line that's on the residual plot. There are three particular things we're going to want to look for on the residual plot. First of all is we want to have a consistent spread all the way across. Second thing is we can't have any kind of pattern to the residuals, and we'll talk about what that means and look at a couple of examples. And thirdly, we can't have any influential outliers. Outliers aren't the end of the world, but we can have any that are this quote-unquote influential. And again, we'll talk about what that means. Let's dive into the first one here. Consistent spread. We must have a consistent spread. So if we look at this example, you can see if we put a little bar across your little shaded region, they're all pretty much equally spread across the graph. That's what we're talking about when we mean consistent spread. So what might it look like if we don't have a consistent spread? Well, here's our original data. Let's say we have some data that looks like this. Still looks pretty linear. If we make the residual plot, it looks something like that. But now, not so straight. Now it actually looks like it starts to spread out. As the x values increase, the residuals actually increase. So this one does not have consistent spread. Okay, that's number one. Second thing we have to have is no pattern to the residuals. So again, let's mess with our original one. Let's say it looks something like this. Now, a linear model kind of fits. It's pretty close to the line. If we look at the residuals and make the residual plot, though, pretty clear, like parabolic curve or something there. So there's patterns in those residuals. That's not good. That means a linear model is not good. So that does not fit for this particular set. Okay, the one that's the most complex is influential outliers. The big question is, what does it mean to be influential? We're going to look at three specific types of cases. First one is this one out here. We have one kind of, it's on the line. It kind of goes in the same direction, but it's an outlier. The key is we have to compare the equation with that point. So here we have a slope of 0.36 and then a y-intercept of 3.31. And then take it out and then find the equation again. And you can see they don't change too much. 0.36 versus 0.33. I think it was 3.31 for the y-intercept. Now we have 3.41. Not really a big change. So that point we would consider, yes, it's an outlier, but it's not influential. All right, let's look at another one. What if we have one in the middle here? Again, kind of jumps out, a little bit of an outlier. Again, we'll look at the equation with that point in there and then take it out and see what the slope and y-intercept look like here. It just kind of shifted down a little bit. Slope didn't change very much. So again, probably not influential. One of the keys that made this one not influential, even though it was far off the line, is that there were a bunch of points underneath it kind of counterbalancing its effect. That first one way out here, yes, there were none near it, but it was right on the line. This one, it's pretty far from the line, but there's a bunch of other ones near it that kind of counterbalance its effect. Okay, so last example, what if we have one way over on that bottom left down there? Here it is, here's the line with that point in here, slope of 68 hundredths, 1.84 is the y-intercept, and then if we take it out, look at the change now. Like about a 50% drop in the slope. Big change in the y-intercept. So that one is influential because taking it out significantly changed the slope and y-intercept of the equation for the least squares regression line. Again, this is the most challenging because there's no hard line for what it means to be influential. It's kind of like a statistician's judgment about whether this is influential or not. Again, the three cases we had, if we have one that's on the line, kind of in that direction, that's typically not influential. Outlier, but not influential. If we have one that's a big outlier, but it's got a bunch of other points near it, that's probably also outlier, maybe somewhat influential, but not significantly. The ones that are the riskiest are the ones that are outliers, but they're kind of off by themselves. Those are the ones that are most likely to be influential. So again, for the residual plot, the three things we're looking for are: first, we want to have a consistent spread. Second, we want to have no pattern to the residuals. And then third, we don't want to have any influential outliers. What we want to talk about now then is how to get this residual plot within StatCrunch. This is in the regression menu. So we'll have our education data. I'll put that link in the description again. And we'll just go stat, regression, simple linear, just like we've been doing for all this analysis. And then if we scroll down, we've got our kind of basic stuff here. There's a specific plot. Now, what's tricky here is there's multiple plots that have residual in the word. And so some students think, oh, it's just in StatCrunch. I'll just remember which one it is. And you just get confused. And inevitably, I can tell the students that haven't studied. So you have to remember what a residual plot is. It's residual on the y versus the observed, the actual x value. So that's the graph we want to pick. We hit compute, and then we can go and see that residual plot. If we want to, we can modify it. If we need this for a test or a presentation, we can add a title, clean up the labels, etc., just like we would for a regular graph. Okay, now that we have our residual plot, let's take a look and see if we meet those three conditions. Remember, we want consistent spread, no patterns to the residuals, and no influential outliers. So let's take a look at that first one, consistent spread. This is what we want. We want it pretty even all the way across. This one isn't bad. There's this lump at the top. Those are actually a bunch of selective schools in Chicago. We've got a couple on the bottom. We've got this lump over here on the top right. So it kind of looks like it might be curved there, not a consistent spread, but it's not as exaggerated as I've drawn. You know, it's not perfectly spread, but it's probably reasonable here. I think it's reasonable to say that there's a pretty consistent spread to this one. Remember, there's 3,500 schools, and so you have a few here, a couple here. That doesn't blow the whole model just because there's a couple. Now, for the pattern, this is the one where we're problematic, right? We've got some at the beginning that are above, in the middle they're below, in the end they're above. That kind of gives us that swooping when we look at the residual plot. So it's not great, but again, it's acceptable for this one. The last thing to look at is outliers. So we have these 5 up here, and we have a couple low ones. All of these are really not going to be problematic because there are so many points in the middle there that kind of balance out their effect. In fact, if you look at those 5 that are above, those 5 are actually selective enrollment high schools in Chicago. You have Lane Technical, Jones College Prep, Young Magnet, Northside College Prep, and Peyton College Prep. Actually, if you look at the criteria for these, you actually have to have certain scores and be kind of top performing before you can even get into those schools. So of course they're going to have really high SAT math averages compared to their low income density. So those are not really representative schools. In addition to the residual plot, there's more we can do just from the output of this regression model. If we focus on the top part here, we've talked about a couple of parts here already. We have the correlation, that's the negative 0.7, pretty strong negative correlation. We also have the least squares regression line. And then below here, there's this R squared. R squared. It's called the coefficient of determination. And it is really important and gives us some really specific meaning about how good the model is. So it's calculated literally just by squaring the correlation, R squared. What it means is it's the percent of variation in the response variable that can be explained by the predictor variable. So for our example, it's about 0.48. That's 48%. So that means 48% of the variation in the SAT math average can actually be explained by what percent of the students in that school are low income. That is actually really good for a model from real data that you can explain almost half of the variation in a school's SAT score, average SAT score, just by knowing what percent of the students are low income in that school. That is really good for a model using real data. That's not actually that common to get an R squared almost 50%. So again, the coefficient of determination, that's R squared, it's always interpreted this way. It's the percent of the variation in the response variable that can be explained by the predictor. So if you're one of my students, you're taking notes, be sure to write this one down. This is super important. All right, let's talk about some examples and show some analysis that we might do on these examples. The first one we're going to do is in the LGB Life and Health data set. I'll put that link in the description. We have the age that they told the family their sexual orientation, and then the age that they told the friend. It seems like those would be very strongly related. Here's our output. If we look at the correlation, pretty strong, 0.846, right? Very strong. R squared, 72%. So 72% of the variation in when they told their family can be explained by when they told their friend. So if you know one, you pretty much could predict the other one based on the model. If we look at the scatter plot, it looks like this. We do have some outliers. There's so many other points near there. They're not going to be influential though, so I didn't even bother taking them out of the data and checking that slope. The residual plot looks like this. But we're supposed to have a consistent spread here. This one is really bad. It's like spread out in the middle and then very condensed over at the end. So that is not good at all. In fact, the reason what's happening here is this was a survey that was taken at kind of key points in lives. They looked at young LGB, like not middle age, but like in their 30s, 40s, young for, and then in the 50s and 60s. So it's not like it was equally spread out. It wasn't a representative sample of all LGB adults. This was for this particular survey. They were looking at comparing responses between age groups. So the problem here is we're just getting less data on those high ages because that was the sample. So we probably shouldn't be relating and looking for relationships between ages just because of the source of the data. Another one from the education data, a lot of people talk about class size and how important smaller class sizes are. So you might say, well, I wonder if there's a relationship between the SAT math average and the average class size at a school. So here we look at this analysis. Look at the R and the R squared. Not really. It's only about 10%, right? And then check this out. Here is your scatter plot, and then here is your residual plot. We're supposed to have consistent spread. No, we do not have consistent spread. Okay, a linear model is definitely not appropriate for that at all. That's really bad. So this one is clearly bad. Like our other one, remember, it's like not great, but not as extreme as this. All right, that is it for this particular video. Hope this was helpful to help you understand how to determine whether a least squares regression model is appropriate. If you enjoyed this and want to see more, you can subscribe, hit the bell to get notified. Also, I want to give a big thank you to the Elgin Community College Board of Trustees who approved my sabbatical during the spring 2021 semester. And that's what gave me time to do all this recording and editing and producing and uploading these to YouTube to share with you. So thank you so much for watching, and I will see you in the next one.